All right. Welcome back, everyone. I'm gonna be solving today the famous N Queens puzzle. The 8 queens puzzle, but also for other sizes, for other numbers of queens. This is a classic of classics, and as you might see from the hello Goku, welcome. Yes, we are going to do the N queens, but I'll try to teach new things. Even though this is a classic of classics, I'll try to teach it some nuances that you might not have learned before. So yeah, let me read the problem statement. Let's go. Hey, not Sean. Thanks for the follow and for the nice words. And Smart Coder is here as well. Thank you. So the problem is a problem of placing n queens on an n by n chessboard such that no 2 queens attack each other. And we have to return, given the size of the number of queens and the size of the board, we need to return all the distinct solutions to the puzzle. And it doesn't matter in what order we return them. And here they specify how we should represent the board in the solution. So we should put a Q letter for representing the queens, and a dot for empty space, empty how is the name? A square. Okay. Anyways, we get an example, only 2 examples. So for this trivial case, we only have a board of 1 by 1, and there's obviously only one solution. And notice that for n, so this is up to n equal 9, which is a small number, seemingly. But as you may know, we will be using backtracking to solve this, and usually backtracking solutions are exponential in time, so that's why you usually cannot solve big size problems. But yeah, let's start working out. So in this case, we are asked to return all the configurations, but there are other versions, there are other variations of the problem. One of them is to count how many there are, or even to say whether it's possible if there's any solution, because as you will notice, for some sizes it cannot be done, there's no solution. So in this case we should return an empty list. So let's start by working out. So for example, for 4 there are 2 distinct solutions to the 4 queens puzzle. So maybe we can work them out. So notice that these 2 solutions are kind of similar, right? Because if you rotate if you rotate 90 degrees clockwise, well, I think you also have to mirror it or reflect it, and in that case they are the same solution. So that means that they are symmetrical, but it doesn't matter for this problem. But let's start working out some examples. So let me grab the pen and all right, so let's say we have n equals 4. So yeah, or maybe even for n equals 2, it's pretty obvious if you think about it that there are no solution, because so if you place one queen here, remember that queens, if you don't know how to play chess, queens attack horizontally, vertically, and diagonally in all directions. So yes, if you place a queen here, you obviously cannot place a queen in any other. I mean, queen is attacking here, here, and here, so you cannot place another one without them attacking themselves. So for n2 we have to return an empty list. And so what happens for n4? So let's start. How would we solve this by hand, for example? So let's say that we place a queen here, right? So then that means that, so we're trying something randomly. Let's say for the first row we try the first column. So that means that here, all this column and all this row now are attacked by this queen, so they are forbidden. So now notice, if we place the queen here, then we will attack this two, this place and this place. So then we would not be able to put any queens on the third row. So yeah, maybe I did not clarify this, but notice that we can't place one queen per row. So, and we have the same number of queens as rows, so we obviously have to place one queen, exactly one queen on each row. So if we place it here, we won't be able to place a queen in the third row, so let's try it here. So that means that now this is taken, or this is attacked, this is attacked, and this is attacked. So now we only have one option here, but now this is attacked and we cannot place a queen on the fourth row. So that means that we failed to place to find a solution when we started from here. So now what can we do? Well, we can backtrack, which is the magic word here. So notice that when we place the only choice, once we place the first queen, then it was pretty forced where to place. We said, well, we cannot put it here, put the second row queen here, so we have to put it here, and then we were forced to put it here. So let's try the second. Let's backtrack and try the second option. It's as simple as that. So what is the second option? Is here. So we're going row by row. I mean, it's the same going column by column or row by row. I just chose rows arbitrarily. So now these are attacked, And so, well, wait. This is also attacked because of the diagonals. So now we are forced to place the second row queen there, which is the only one. And so now this is attacked and this is attacked. And so now we are forced to put this here. And now this is attacked. And we found a solution, which is one of the solutions in the example. So cool. So cool. So this is a win. So how do we do this with a computer? How do we do this systematically? The same thing that we're doing manually, we can do with a computer, which it's dumb, but it's very quick. So we can do all these trials and errors and backtracks by writing a program. So one thing first, notice that so let's count how many possibilities there could be, or at least find an upper bound of the number of configurations. So notice that for the first row we have n, well, in this case we have 4 possibilities, right? But then for the second row, let's forget about the diagonals for a moment. So we cannot put it in the same column as the first one.
Here's what I found.
Oh, thank you very much, Creepy Pasto. That's high praise, thank you. So 4 possibilities for the first one, then we have 3 because one column is occupied by, it's attacked by the first one, and so on. Then there are 2 rows that are attacked by the previous ones. So, and how much is this? This is 24. So that means that we only need to check 24. I mean, here we were also taking into account the diagonals, so that's why we did not have to check so many configurations. But so in general, this is the n factorial, this product. So the number of potential configurations are bounded by n factorial, and here we have up to n is between 9 and 1. So in the worst case we'll have 9 factorial potential configurations, and that is not such a big number. I mean, the factorial function grows very quickly. Once you get to 20 or even 15, the numbers have like over 20 digits or more, which is untractable if you want to go over all those configurations. But in this case it's only 9. So let's see. So I know by heart how much, what this number is. I think it's around 300,000. Not exactly, but approximately. Let's see if I'm right. So this is 9 factorial. So yeah, it's 360,000. So this is approximately 10 to the 5.5. Like So I taught how to do this. Why is this true? Because this is approximately 300,000, which is this, but 3 is 10, approximately 10 to the 0.5, so that's why we add up the exponents and we get this. So anyway, so this is 300,000. So even if we went over all the configurations without doing this filtering, we could do it in time. So let's see how we can do that. Okay, so we are going to use backtracking for this. So let me write this. Maybe I can move this a little bit to this side. Okay, I want to show this number, which is the one that we computed. So, hey, the zombie killer whale, welcome. We are working on a classic of classics. So, okay, so you can think about this process that we did here by hand as a tree, as a decision tree in some sense. So initially we have this root node of the tree, okay, which corresponds to an empty board. So this is the empty board. All right. So now we have 4 decisions that we can make, right? We can put the first queen, the first row queen on the first column, or the second column, or the third column, or the fourth column, right? So that means this has 4 children. And so this, I'm not going to draw it all, but I want to draw at least one. So here it means that we chose to put the queen here, right? And here, so I mean this is important so that you understand the recursion of the backtracking. So here we chose, so this node corresponds to this board where we chose the first column of the first row, and so on. So here, sorry, which is supposed to be black. So here you will have 2 other boards, and this is the second. So here let's say that we chose the first, the second, the third, or the fourth row. But now when we follow this path and we place the first queen in the first column, then we only have 2 options for the queen in the second row, right? Because the first column and the second column are attacked. So that means that this node is going to represent a board that has a queen here and has a queen here, right? And this board is going to represent a board that has a queen here and a queen no, here. Let's correct that. I make dumb mistakes sometimes, but it's okay if you correct them. Alright, so you get the idea. So yeah, maybe this is interesting. These 2 middle nodes are interesting because putting the first queen on the second and third columns, and in that case the second row queen is forced. There's only one option, so that means that this is going to have only one children, and this is only going to have one children, and this. So notice that these are the same, right? But well, it doesn't matter. Anyways, so eventually, so here we went down one level and we had one queen. Then we went down another level, we had two queens placed. So here we're gonna have 3 queens, and here we're gonna have 4. So this is going to represent a solution. So all the leaves here, well, there are only 2, right? But at this level we're gonna have the solutions, because we have to move down 4 times for the board to be covered. So what are we doing when we, so this is analogous to the recursion tree of the backtracking. So this is exactly what we're going to do. We're gonna start with an empty board. We're gonna try putting the first queen in the first row, and we're gonna try with the first column, second column, third column, fourth column. For each, we're gonna then call recursively, which is the same as going down this tree, and we're gonna try putting the second either in the third, on the fourth, and so on. In practice, we're not gonna know initially whether the first and the second columns are already attacked. We're gonna consider all of them, and we're gonna filter out the ones that are invalid. So finally we're going to make calls only for so on, and we don't have possibilities, like for example when we worked out this case, so we failed, and so then we're gonna backtrack, which is done automatically by the recursion, right? So that will mean that we found a node, and we go back without adding any solution, and we go back here, and then we continue putting here the second queen on the fourth row, and then we go down, and then we fail maybe, and we start going up, and so on. And that's essentially what we're doing when we are backtracking. We use the recursion as a way of trying systematically all the possibilities, and when we find out that there is no solution with the decisions that we made so far, we go back and we keep trying the other solutions. Okay, so that's essentially what we're doing when we do backtracking. So then there is another thing that we do, which is that when we do all this recursion, we are going to keep track of the state of the board, and not only the state of the board, but also it will be convenient to know where we have placed all the queens that we have already placed. So that's gonna help us know whether we can put the new queen, the current queen, we can put it in each position. We're gonna check if that position is already attacked, and in that case we're gonna skip it immediately, and we're gonna only go down, try the positions that are not obviously invalid currently. But the point is that we are going to keep this state, which is not going to be copied. We're gonna keep one um, only one copy of the information of the board, and we're gonna modify it. We're gonna try putting the queen in one place, so we mark that as a Q, and we push to a list of all the positions, the current coordinates, and then we move down to the next. And then when we finish trying one possibility, we will undo our change, so that we can then try another option, but we undid the previous one, and so on. So the code is pretty generic. The backtracking code, the structure is the same for many problems. So let's say that we call it find well, let's call it just find for simplicity. And we're gonna get the board and the queens, the positions of the queens that we have already placed. And so, well, and also we want to know, I mean, we can know this by, we want to know what the current row is, and that's going to be the length of Q, which has the queens that we already initially, we don't have any queen placed, so this is 0, which is row 0. That's correct. So if R is equal to n, we are done, and that means that we return B as a list with B as the only solution for this state. And then otherwise we want to go over, so for all the columns, we check if it's valid, taking into account the queens that we have placed already. Is it attacked by any of them? And if it is, then we are going to find, so we are going to first add it. So yeah, let me correct this. We are going to add this to Q. So we append the row and the call. Then we call find of B and Q, which are the same instances. And then this is important. Then we're going to pop. So we are going to undo the append, because we then want to try another column, so we need to undo this. So this is the structure of the code. We need to then fill out the valid function, but we're gonna think about that in a moment. So all right, so let's define our find function, which is going to have the board and the queens, and if the length So yeah, maybe we can put it here so that we have the n handy. So if the length of the queens is n, it means that we have already placed n queens, so we return the board. But there's going to be a catch regarding the board. So eventually we're gonna call find, and we're gonna call it with a board, an empty board of size n rows, and this is the empty square, and we want n columns, so that's an empty board and an empty list of queens. But here there's a catch, because they ask us to return the board as a list of strings, not a list of lists. So that means that we need to, let's call this translate board, so that we keep it encapsulated. This is more of a Python thing, don't worry about it. So we want for row in board, we want to join to get a string for every row. So that's it. Anyways, forget about that. So now we want to check. So we are in the row length of queens. Initially we're in row 0, and we want to consider all the columns, and if it is valid, which means that it's not tagged by any of the already placed queens, then we are going to add it. We're going to find the solutions for this new state, and we're going to remove it. So notice that okay, maybe we can just no, let's not do that. Let's do it recursively, as we should. So find is supposed to return a list of solutions. So this should return the same as this, because that's what we are returning here. So that means that, so here in the base case, we are doing exactly that. We are returning a list of this, which is going to be a list of strings. But what do we do here? Well, we are going to keep track of a list, and we are going to extend it. How do you guys have any Discord? Yeah. Thanks, Goku. Okay, so we are going to add all the solutions that are defined by this call. We're going to add them all to the result, and then we're going to return all the ones that we have found, that were found by our children. So now we only have to implement valid. Okay, so we have queens, and we have the row and the column. So we want this to not be attacked. So for all the row 2 called 2 in queens, we want this to not be attacked. So yeah, not attacked, let's say. Row call. Okay, let's do it. Let's break it down. Why not? So when are they attacked? Well. So one possibility. So we know that the row is not the same because that's how we are constructing the cases. We're putting one on each row. So we know the rows, but the columns could be the same. So if the columns are the same, then they are attacking themselves, or they could be attacked diagonally. So for that, what needs to happen is that the distance between the rows has to be the same as the distance between the calls. Okay? So that's what it means for this to be in the same diagonal. Notice that I'm saying distance. Why is that? Because if you think about it, okay, let me draw it. So if you have this square, right, which let's call it, let's call this R and C, this coordinates. So if you have another square in the same diagonal, that means that the distance, if it is in the same diagonal, then the distance here, which is, let's call it the delta R, is going to be the same as the delta of the columns. Notice that when I'm saying distance intentionally, because this is also true. Distance is measured by the absolute difference. So if you want the distance between R1 and R2, which are two rows, you compute the difference, but the difference could be negative. So you use the mod, which is in Python you write like this, and in many languages. And why is that? Because if you have, if this is R1 and this is R2 and this is column 1 and this is column 2, and one queen here, and the depending on the order, but here the distance from the DR is going to be 2 and the CR is going to be 2. And notice if you move along this diagonal, that means that you have to add 1 in the rows, all right, or you have to move 1 in the columns. So that means that the distances are both going to be increased by 1, and that's why if you move within the diagonal, this condition will still be true, that the distances are the same. So that's why we use this expression. Okay, so yeah, let's try this out. All right, we got, oh, so we did not update the board, which is a little detail here. So here, so the board, we want to set it to a queue. So we can add an assert here. We know that we don't have any queen in that row, so this square should be empty at this point. Then we put a queen in it, and then we remove it. So we put it back as it was, and that's gonna do it, I believe. Oh, so I call this row and so usually test, or I want to be more are as names, but here I'm gonna as readable as I can. So okay, so this solved the problem. It's not too fast. So can we make this faster? I'm glad you asked. So notice that here in valid we are going over all the queens that we have placed. So that means that we are potentially going over 9 queens in the case of n equal, well, 8 queens, let's say, in the case of n equals 9. So maybe we can skip that. So for example, to know if the column is already occupied, we can say a free column, and we say that initially it is true for all the n's. So here we can say, so if the column is free, and then we have to change it as not free, and then we put it back as it was in the end. So this is the standard. We change the state and then we put it back as it was. So why does this matter? Well, we are now checking whether the call is free by just accessing this array, which is O of 1, whereas here we can now erase this. Here we're checking the call by going over all the other queens, which is O of n. I mean, it's a little misleading to say order of n here. Well, I mean, it makes sense theoretically, but this problem has been solved. So yeah, this is an interesting. Maybe you want to read this. So one thing to note is that this is a classic problem. It's a very well-known problem. It's been studied for decades or even centuries. So it's okay when you find a problem that you suspect that it's well known, then it's okay. Your first instinct would be to search for information and start reading about it. Even in a contest, it's valid. It's fair. So yeah, so I found this table interesting. So here we have all the solutions for every size for the number of queens, and notice that the table has goes up to 27, and that is because so that is the highest order board that has been completely enumerated. So that is very interesting. Notice that in the whole world, in history, no one has been able to enumerate the 28 queens problem, right? So maybe you can do it. Maybe with the advancements of and the improvements on the speed of the computers, or maybe by having a distributed system, you can solutions, or you can count them. I don't know if exactly if so this is the exact number of solutions, but then there are approximations, or there are functions that approximate the number of solutions. Anyway, so that's a side note if you're interested on what is known about the problem. Okay, going back to this. So we were trying to optimize this. So now we are able to check the columns, the free columns, in order, in constant time, just checking an array. But we still have to check so yeah, let's run this, make sure that it works. And yeah, it seems to work. You can submit it, but we're still checking all the queens for the diagonals. So we're still doing a for loop over the queens. Can we do the same, but instead of for columns, also for the diagonals? Well, the answer is yes, but it's a little more complicated. So we want to. So there are many ways to do this, but we want to, for a given row and column, we want to represent it, to be able to have a representation of the diagonal that it's in, right? So, for example, notice if we are interested here in this position, so this is R, this is C. So first notice that this belongs to two diagonals, one in this way and one this way, right? So let's start by focusing first on these diagonals, the ones that go in this way. So we want a number. So we want for all the positions that are in the same diagonal, we want to have one canonical representation, one class. So one way to do this is to do this, to do the difference of the coordinates. So we're gonna have a function that, given a position, it's going to give us some number that identifies the diagonal. Okay, and we want that number to be the same for all the positions that are in the same diagonals. And why does this work? Well, if you think about it, it's similar to what we done there to see if they were in the same diagonal. So notice that if you are located at one position, and when you move to the next, you are incrementing the column by 1 and the row by 1, and that's how you move within. You move to the next one, in one sense, in this diagonal. So notice that if you increase the row once and you increase the column once, this will remain the same. This will be invariant, and that's why when you move along this diagonal, this number will be the same. So that's one property that we wanted about this. So for this, for this, for this, for this, and for this, you're going to have the same numbers. And notice that, for example, if C is 0, if we are on the first column, then this number will be determined by the row. So it's going to be 0 for row 0, 1 for row 1, 2, and 3. So that means that this diagonal will have number 3 to represent the diagonal. Then this diagonal will be represented by number 1, and so on. But so that was for the case where C was 0. What happens? So if C is 1, so what happens with the rest of the diagonals? Well, in this case, this number will be -1, and then -2, and then -3. And these are the numbers that will represent these other diagonals. But since we want to use this as an index in an array, which has to be from 0 based, so the minimum number is going to be negative n minus 1. So if we add this n minus 1, then we shift it and everything is going to be from 0. So this is going to be within 0, and the maximum number is going to be when we don't subtract anything, so C is 0, and when R is n minus 1, and that's going to be 2 times n minus 1. Correct? Because this is cancelled. We have an R. No, sorry. This is going to be up to 2n minus 2. So the size of the array is going to be 2n minus 1. Yeah, that's it. And so, and the same idea goes for the diagonals on the other side. Let's call them diagonal 2. But instead of using the difference, you use the sum. So you translate a position from R, from this pair to this number, and that's going to give us a number that represents the diagonal in this way. And this doesn't have the problem of being negative, and it's also going to be from 0 and to n minus 1. So that's how we optimize the diagonal checks. So we do the same. So free diagonal 1, it's going to be true initially, and we're going to have 2n minus 1, and free diagonal 2 is going to be true initially, so same thing here, and here we want this free diagonal, and we use the function that we assigned. So diagonal 1 is going to be r minus c plus n minus 1, and the free diagonal 2 is going to be r plus c. And if they are all free, we're gonna set them as occupied, as non-free, which is false. And then in the end we're gonna free them again when we undo this, and so we can drop this now, and this is going to work. Okay, so I forgot about the naming. So this is roll call and row call, and the same here, and this is row call and row call. Let's see. Let's see if it's a little faster, and yes, it's now bits 84%. So it took, the first one took 115 milliseconds, the second one 72, and the third one 53 milliseconds. So it's a nice improvement. And do you have any questions? I think this one is pretty optimized. Oh, one more thing. Yeah, one more thing that I can explain is yes, when we go here. So what is the difference between backtracking and programming? So why can't we use programming for this problem? So here's the thing. So the difference is that there are no sub-problems. Like we said, when we are making cases of our solution, so if we are here, our next choice depends on the whole path of all the previous decisions. That's why we needed to keep track of all the places, the coordinates of the queens that we had placed before. So in other words, we need to know the whole path. And that means that the problems don't overlap. So each problem depends on the whole history. So you cannot forget, in some sense, anything. When you do dynamic programming, you are only remembering what's relevant to solve the sub-problems, and so you are forgetting all the irrelevant details. And that is why it would not make sense to another way to think. So you could it's the row. So I forgot. Yes, we don't need this anymore. Now we only need to know the current row. So we shouldn't be using that, and here we start from 0, and yeah, that's a little cleaner. This is not needed anymore. It's not needed anymore. Okay, maybe this makes it a little faster. Well, seems so. Maybe it's measuring error, but we'll take it anyways. So going back to this, I was saying that yes, what characterizes? Can you help me understand simple math? Not right now. I'm gonna try to finish this, but do you have a specific question? So what characterizes a subproblem here? Well, we are remembering all the columns that are occupied. So now we are not exactly remembering all the positions of the previous queens. We are remembering only what rows are free. For example, what columns are free, right? So that means that we could do a bit mask with that, right? So we could say, okay, here. So if we are here, that means that column 1 and column 4 are taken, are already attacked. So if we say which ones are free, then we can have this mask, right, that says that only the 2 middle columns are free. And so we would have a way of, with n bits, we can encode which columns are free. So great, we can use dynamic programming with a bit mask. So what is the problem? Well, the problem is that we have another one. We have another one for the diagonals, which is bigger. It's, in this case, it will be of size. So this is size 4, but the other one is going to be of size 7 because there are 7 diagonals. 1, 2, 3, 4, 5, 6, 7. So we're going to have another bit mask here, and then another one for the diagonal 2. So in total, we're going to have 18 bits. And that's a lot. That's too many bits. So that is because the problems do not overlap. There are too many subproblems, and that's why it's not advantageous to use DP for this problem. So that's an interesting and a nuanced point, so that you can relate backtracking to dynamic programming and understand why you should use one for one problem and the other for another problem. So remember this concept of overlapping subproblems. That's critical to know whether you should use the P. Of course, in most problems you will have a hint by the size of the input. When the size is very small, that's a hint that you should use backtracking. And so one other point. Notice that here we said, well, there are 10 to the around 300,000 configurations, potential configurations, right? Because we only cared for columns and rows. We did not care about the diagonals. We simplify it so that we could count it easily, and we said, okay, there are around 10 to the 5.5 configurations. But so one algorithm could be to generate them all. So how could we? So in Python there is a permutations function. So I guess we could code that from scratch. Okay, let's do it. Why not? So we have a configuration permutations of. So this is going to give us the call for so I'm connecting out of chat. Can you hear me? Anyway, so we can try. This is going to give us, and if it's valid, then we generate from this, and so, or let's call it translate. So this would give us a, so for every row so n is the length of the call. So for every row here, the column is going to be call of row. So that means that we are going to have a string So yes, let's have a matrix here, and we want this, and we want row and the call for this row to be a queue, and then yeah, so this is actually the board, and so that translates one representation to the one that we're asked to generate, and then we want to see for if it's valid. So for every no pairwise, no. So let's check every pair here. And if, so this is going to be no, this is row, and this is the column of the row, and then this is row 2, and this is the column 2. And so if C2 is equal to C is equal to C2, or so this is the same that we did before. It's not valid, and otherwise it is valid. So yeah, that should do it. So I forgot here to close this, and so this worked. Surprisingly, I thought it would be too slow. So do you understand what we did here? We just went over all the permutations that are this number, in the case of n equal 9, and we generate them all. So this means that for every row we will have a different column number. So then we just check all queens between all pairs of queens. We see if they are attacked, and in that case we say it is not valid, and so we filter based on that, and then we just translate that representation into the representation that they ask us to return. So this is what it's called. It would be called like a brute force search, where we are enumerating all the possible solutions, but then we're filtering out the ones that are bad. And why is it different than backtracking? Backtracking is better than that because we're doing the decisions in some order. We're doing decisions, and we are checking before we fill the whole. We made all the decisions. So that means that we are, in a sense, we are pruning this tree. So for example, here we had only one child, but if we did it the brute way, if we would have 3 children here, because we had 4 here, and then we should avoid only the column number 3. So then we would have to choose 1, 2, and 4. So instead of 1, we would have 3, and that will make the tree bigger. So here we know that there were only two solutions. So when you get to the last level, to the leaves, this tree will only have two leaves. Well, not two leaves, but two nodes at that level. Whereas the whole tree without pruning will have 4 factorial, so 24 nodes at that level. So that's why backtracking, even though it's a kind of brute force, so it is exponential, it is better than n factorial in this case, which is the more brute force approach of enumerating all potential solutions and then filtering out the ones that are bad after we have generated them all. So yes, that's all I have. I think we went over many concepts of backtracking, so I hope you learn from this. I don't think usually the presentations of this problem go over all of this, so I hope you learn something new, even if you knew this problem before. I hope you find something original here. So that's my goal. So that's all I have. Thank you for watching and see you in the next one. Bye bye.